Good afternoon, everyone. Thank you for joining our technical webinar. Today at Diana, we are very happy and proud to have as a guest lecturer, Mario Pimentel. He's a prorector of the University of Porto and assistant professor of the Faculty of Engineering, and a long-time Diana user and experienced user, I would say. And today it's really a pleasure to have him as a guest, and he's going to discuss an interesting topic, which is the tensile response of ultra-high performance fibre-reinforced composite concrete. So that's very interesting. Before we start this session, just a couple of points. As usual, your microphone will remain muted to avoid any background noise disturbance. But there is a chat box where you can ask your questions. So I will be monitoring this question box, and at the end of Mario's presentation, I will raise the questions that are, let's say, interesting for the whole audience to him, and eventually he can answer on the fly, or we get back to you later per email. This session will be recorded, and after a review of Mario, we will decide to publish it on our social network. And as always, you can at any time just also send questions to me directly if you have a question that are not related to the presentation itself. Having said that, I'm going to hold the presentation to Mario. So Mario, if you can unmute yourself, the stage is yours.
Okay. Hello, everyone. Thanks, Jean-Claude, for the introduction. So my name is Mario Pimentel. I work at the Faculty of Engineering of the University of Porto, and I'm very happy to be presenting for you today our work that we've been developing, I would say, for the last 10 years, maybe, on the tensile behavior of UHPFRC. So first and foremost, I would like to acknowledge all the persons that contributed to the work that I'm going to present to you today. It's far from being a work from a single person. So I'd like to thank Sandra Nunes, my colleague, who really started this research line here at Porto back in 2014, maybe, in this project over here, and then Amin Aprishambav and Amat Areusin Ruivalent, so all the researchers that contributed a lot to what you will see here today, and also to the laboratory staff that did a lot of work on the experimental part of what I'm going to be describing. So, what is UHPFRC? That's I would like to start here. So, it's an amazing material, actually. So, it's in very simple terms. It's composite, which has a cementitious matrix, and fibers, which are usually steel fibers. So the matrix, you can develop your own, but it's readily available today as premix that we can acquire. So typically the matrix is constituted by cement, silica fume, and then other supplementary cementitious materials like fly ash, limestone powder, many options we have. So the water binder ratio is very small, below 0.2. And of course, we need super plasticizers and other mixtures to make the material self-compacting, which is also a very attractive feature of this material. So it's flowable and doesn't need vibration. So to have the properties that we need, typically we have to introduce a large amount of steel fibers, so much larger amount than standard fibre-reinforced concrete. So usually short steel fibers, as you see here, and typical dosages between 160 and 320 kilos per cubic meter, which corresponds to fiber volumetric fractions between 2 and 4%. So the mechanical properties are really distinguishing. So this material really stands out from conventional concrete. So the unit weight, it's not much heavier than standard concrete. The compressive strength in typical compositions can vary between 130 to 200 megapascals without heat curing. If we have heat curing procedures, we can get higher values sometimes. Yeah, so it has a high limit of elasticity. So the stress at first cracking can vary according to the composition, but typically between 7 and 10 megapascals. And depending on the fiber content, we can have tensile strength, post-cracking tensile strengths that can go up to 16. You can see larger values. These are the most typical ones. So besides this, one important thing is that with the proper fiber content and orientation, as we will see, the material can be strain hardening in tension, as you see here in the green curve. Okay, there are other type of cementitious composites, the different families, which have much larger, much longer hardening branches, but typically associated to lower tensile strength values, which are suitable for different applications. So here it's a very, here in the picture, you see a very distinguishing feature of UHPFRC under tension, which is the ability to form a very dense network of micro cracks that sometimes we cannot see them with the naked eye. So typically here what we do, we spray some alcohol and then the cracks reveal themselves while the alcohol is drying. And here you can see, so this is a UHPFRC layer subjected to tensile strains exceeding 2 per mil. So, and you see here a very dense array of cracks with spacings that can reach about 20 millimeters in this case. So another important property of UHPFRC is the durability. So due to the very low porosity and low permeability and sortivity of the very compact matrix, it's extremely resistant to chloride penetration, extremely resistant to carbonation. So it's a good material to apply in very demanding environmental exposure to the conditions. But some of these properties, some of these durability properties depend on the tensile behavior. If you have an UHPFRC that is capable of forming this tight array of cracks, then it means that it can maintain its durability properties even under large tensile strains. So applications. So this material is being used with success for strengthening and rehabilitation of existing structures, in structures under severe environmental exposure conditions, in structures of high architectural value, because the fibers can replace the reinforcements in many circumstances. So you are free to mold almost any shape that you like in the bridges, like what I show here in precast elements. Here at Porto, we had a recent project where we tried to validate the concept of using UHPFRC in the hugging bending moment region of precast bridges. Precast elements, so I see a lot of applications in the precast industry. Some pictures here on the right from two companies, one in Europe, another in Asia, and etc. So too many applications are possible today. So the contents of my presentation will be as shown here in this slide. So I will start by making a description of the tensile response of UHPFRC based on what we see in experiments. Then I will discuss how we can describe fiber orientation, because as we will see, fiber orientation is very important to the tensile response. Then I will show a meso-scale model that is able to predict or to simulate the tensile response of the material. And finally, a non-destructive test method that we can use to get the properties that we need to feed our models so that we can get the tensile response that, as I will tell you, is a function of the fiber content and fiber orientation. So the tensile response of UHPFRC, it's well illustrated here in this plot. So all these curves have been obtained with the same cementitious matrix, same types of fibers, but different fiber contents and different fiber orientations. Okay. So typically, if you want to do a structural analysis or a finite element analysis, you can model this behavior by a bilinear. It's sufficiently accurate to have a bilinear law here up to peak stress. And so this part of the constitutive law describes the behavior, the tensile versus strain behavior of the material before you get to the peak stress, because at peak stress, one crack will localize somewhere along the specimen, and then all the deformations will be localized on this crack. So from the peak onwards, we, instead of a stress-strain model, we need a stress crack opening model, like what we do for the concrete. Okay, so in the context of finite element analysis, this part of the constitutive law is independent of the finite element size, while here you need to define a fracture energy and then use the Crackman theory to apply in the finite element analysis using continuum elements. So this curve here, this experimental curve here, has been obtained in the UHPFRC with 3% of well-oriented fibers. So we managed to orient the fibers along the direction of the loading. What do you see here? You see a very tight array of cracks. Okay. Here the spacing for your reference. So if this is 40 millimeters, here we are talking about a crack spacing between 3 and 4 millimeters. What did we observe? So there's the formation of the first crack, then a crack formation stage, and then the material enters in the stabilized cracking stage, in which the existing cracks are opening, but no more cracks can form. Okay? If we have the same material, the same amount of fibers, but now they are not oriented according to the loading. Okay, they are randomly oriented inside the specimen. What do we see? A dramatic change in the tensile stress versus tensile strain behavior. And now look at the crack spacing. Now we see the cracks now have a spacing of about, let's say, 20 millimeters, 15 to 20 millimeters. In this case, it's clear that the localization of the deformations occurred while the specimen was still in the crack formation stage. Okay, more cracks could form if localization didn't stop the process. So in this type of, when we have this type of behavior, a bilinear curve also models the tensile response prior to localization here, but typically an horizontal branch is the good enough to reproduce what we see in the tests. So I forgot to mention, so we just need 3% parameters to describe this curve. It's the ultimate strain at the onset of crack localization, the tensile strength, and the Young modulus of the composite. In this case, this value is different from this one here. So in this case, we have to define a conventional limit of elasticity for our material. So in this case, you see the same mix of UHPFRC, but now with much less fibers, half the fiber content of the previous specimen, so 1.5% only of non-oriented fiber. So what do we see? In this case, the material shows strain softening behavior. So it doesn't have the ability to form the desired array of tightly spaced cracks. So in this case, it behaves as a standard fibre-reinforced concrete, eventually with a higher conventional limit of elasticity, but only one crack forms and only one crack governs the behavior. So in this case, we need a linear elastic branch up to the peak stress and then a stress versus crack opening relation for the post-peak part of the tensile response. So in this case, the post-cracking tensile strength is smaller than the conventional limit of elasticity. So tensile response is decisive in many structural applications and depends on the fiber to matrix interaction. So the way we develop the mix design can be tailored to get the behavior that we want. Depends on the fiber content, which of course can also be tailored in the mix design, but also depends on the fiber orientation, as we have seen. But the fiber orientation depends on external factors that we cannot control when we are designing the mix. So it depends on the geometry of the mold, on the placement process, and on the rheology of the material in the first state. Some evidences here taken from the bibliography. So here, this is a vertically cast panel from which several specimens were sawn to test under uniaxial tension. And you see here the range of responses that was obtained. So this is described in the doctoral thesis of Osterly from the EPFL. And so the same material, same theoretical fiber content, completely a very large range of tensile responses in the same panel. Another evidence, so this is taken from this reference here, where they cast a long panel of concrete of UHPFRC, but they let the material flow since this point over here at the left till the end. And then they cut longitudinal specimens to test under uniaxial tension, diagonal specimens, and transversal specimens. So here we should expect that the fibers are oriented in the horizontal direction. So the blue specimens are expected to show the best tensile behavior. And this is what we see here in the plot at the top. And the most striking thing is that if you cast the test specimen individually in a dedicated formwork, you get a different behavior, which is represented here with a black curve, from what you get in the structure. So this is a very particular aspect of this material. And here, another interesting result is that with what do we show here? So this is the same UHPFRC mix that I described at the beginning of this presentation. So we can see that the black curves correspond to specimens with 3% of fibers and the light gray to 1.5% of fibers, so half the fiber content. What do we see? If we orient the fibers properly, we can have a better tensile behavior than what we would obtain with twice the fiber amount, but with the fibers not oriented. So the orientation of the fibers can have an effect that it's even more important than the fiber content. So to sum up, there's no intrinsic tensile response to this material. So it depends on how you cast, depends on the factors that I've described in the previous slide. So the tensile response may be direction dependent, as could be shown in the tests before. The tensile response of the material in the structure can be different from that is obtained in laboratory tests. And typically, this leads to overly conservative design approaches because the designers need to cover worst-case scenarios. So, which questions do we want to answer? And they're not easy questions. So, can we model the effect of fiber content and orientation on the tensile response of UHPFRC? Can we really get the stress elongation curve under direct tension that we observe in the tests with a dedicated model? Can this model provide us the micro crack spacing? Can we describe an isotropic tensile behavior? Can we use this information for analysis at the structural level to scale up this information? And also very important, can we get information about the fiber content and orientation without destroying my specimens? So using a non-destructive testing technique. So these are the answers that we will try to answer during this presentation. So we need to have a description of the fiber orientation. So this can be very complicated, but at the end, we will need only very simple scalar parameters. So the orientation of a fiber can be described by two angles. The orientation angle, okay? Imagine that the JK plane is your crack, and the theta equal to 0, it's a fiber that is perpendicular to your crack, okay? And theta equal to 90 degrees, it's a fiber that is parallel to your crack, so it's not working, okay? The azimuth, it's the other angle that you need to use to define completely the fiber orientation state. So P here, it's the unit vector in the direction of the fiber, okay? So the most complex and most general methodology to describe the fiber orientation is through it's using a fiber orientation distribution, which has to have some properties that we will discuss, and use some stereological principles to get the information that we need. So a simpler way is to use second-order orientation tensors, which can be also helpful, but even simpler, it's using scalar orientation parameters. And we will focus a lot on this one. So the fiber orientation factor. You have here the definition, but then I will go back to this. So the fiber orientation factor can be seen as the probability of a fiber intersecting a surface normal to the direction I, okay? So a very large value. So with this means, if this is a probability, means that the maximum value of alpha is 1, the minimum value is 0. So if alpha is 0, means that you will not find fibers in your crack. If alpha is equal to 1, this means that all the fibers that you put will intersect the crack. So one interesting probability density function to describe the fiber orientation has been proposed by de Gennet in his doctoral thesis, and it has very interesting properties. So it's periodic. What does this mean? So we cannot distinguish a fiber from another one oriented 180 degrees to the other side. So this is the same fiber. So the function must repeat itself every 180 degrees. So you see here the two angles that we need to describe the fiber orientation, theta, the azimuth angle, And it's also useful to have here a direction of preferential fiber orientation. So the direction along which you will find your probability density function will have the highest value. So the only parameter that governs this function is this Kg factor, which controls basically the degree of anisotropy of the fibers with respect to the preferential the direction. Typically the casting or the flow direction of the material. So physical interpretation of this. So if you put Kg equal to 0 here, this means that the probability density function will have a constant value no matter the fiber orientation. So this can be represented here at the right using these figures that basically these figures, what do they tell us? So the surface, it's defined by this function, and the value of the function, it's the radius that connects the origin of the reference system to the surface. Okay, so here you see that no matter the orientation of this radius of this vector, the radius is constant. So we have here a sphere, okay, constant radius. As we increase the value of Kg, we start having preferential fiber orientation. So you see that the maximum radius, the maximum value of the probability density function is achieved here, or 180 degrees to the other side. Okay, so different representations of the fiber probability density function for different values of Kg. So this would lead to an isotropic behavior. The behavior is the same in all directions. Here it's anisotropic, and here it's very strongly anisotropic. So using some math, we can calculate the fiber orientation factor based on the probability density function of the fiber. So, well, the equation is not simple, but the results are very interesting to analyze. So what does this plot here at the left tell us? So with Kg equal to 0, we have an isotropic distribution of the fibers. So we see that the fiber orientation factor takes the value 0.5, no matter the direction of your crack. Okay, this is the red line corresponds to the fiber orientation factor of a surface normal to the axis X, and the green curve to the perpendicular surfaces. Okay, we see that as we increase the parameter Kg, that leads to increased anisotropy in the fiber orientation distribution. We see that then the alpha values start growing in the direction along which the fibers are aligned, but this comes at a cost that the alpha value for the perpendicular directions decreases. Okay, so this explains the anisotropic response of the material when you have oriented fibers. So you will find more fibers in one direction, less fibers if the crack opens in the other direction. So here it's another very interesting picture which shows us the following. So using Kg equal to 5, so corresponding to this line here, I'm showing here the value of the alpha of the fiber orientation factor along any direction. Okay, here I use as preferential direction of fiber orientation 30 degrees. So you see the maximum value of the fiber orientation occurs here at 30 degrees. But then if you go away from this 30-degree alignment, you see that the fiber orientation factor is decreasing its value. Here, the fiber orientation factor is given by the radius. So this is a polar plot. So can we get this experimentally? Yes, we can. So we can polish and we can cut samples from our UHPFRC elements, polish the surfaces, and do some image analysis that allows us to have some algorithms that count the fibers, and they can even tell us the orientation of each fiber. Okay, so the fibers have a circular cross section. If they are inclined with respect to the polished plane, they will appear as ellipses, and the cosinus of the angle of fiber orientation can be obtained from the diameters, the largest and smallest diameter from these ellipses. Okay, so it can be shown that the fiber orientation factor that we will use throughout this presentation can be obtained through this very simple equation. So the fiber orientation factor in this surface, it's the number of fibers per unit area, okay, times the area of each single fiber, the cross-sectional area of one fiber, divided by the volumetric fiber fraction. Okay, so if you multiply alpha 0 by the volumetric fiber fraction, you have the area of steel per unit area of composite. And then we can compare what we measure in our specimen. So we did a lot of work orienting the fibers, and so that we have a lot of data. And you see here the dots are the experimental data points, okay? And the lines are the predictions of obtained, using this equation. We see that, okay, it's not too bad. So the equation fits well what we observe. Also important, as we will see, is another concept, which is the probability density function of the orientation angle of the fibers that intersect our crack. Not all the fibers in the volume, but the fibers that intersect our. So it can be shown that it's given by this equation. And I show you here some experimental evidence that helps validate a little bit more the probability density function that we are using. So these histograms were obtained from image analysis of polished surfaces of UHPFRC specimens, and then the red curve, it's the theoretical value. And we try to fit the alpha value in our theoretical curve to the alpha value that we got in the experiment. So what do we take from here? That when we have well-oriented fibers, so a very large value of alpha 0, we see more fibers with orientation angles close to 0, which, if you recall, 0 means that the fiber is perpendicular to the crack. Okay, so we see very little fibers with large orientation angles. These fibers, as we will see, are not effective sometimes. Okay, so we see that if the fibers are well oriented, they are almost all effective. On the other hand, if you go to the other side of the spectrum, if you have a specimen with a very poor fiber orientation, okay, you see that you have a lot of fibers with large orientation angles that will not become effective when you start applying tensile stresses to your material. So this leads us to this concept, the fiber efficiency factor. So this will be helpful because it greatly simplifies our mechanical models. So let's assume that we define an efficiency function for our fibers. That depends on how well they are oriented. So this efficiency function can have many shapes, many equations can be useful to describe this behavior. So the fiber efficiency factor is mathematically, it's the expected value of the fiber efficiency function. Okay, so this is the probability density function of the fibers that intersect our crack. If you remember your the calculus, this is the expected value of the function g. So which function should we use then? So we adopted the simplest one. For sure there are better proposals than this one, but this has the advantage that is very simple. what are we considering? So the fibers are effective if the orientation angle is smaller than 60 degrees. If it's larger than 60 degrees, we say that they're not effective, so we will not consider them. So is this reasonable? Well, you see here some results of single fiber pull-out tests that we did here at the lab. Here you have a picture showing it. What do we see? We see that even fibers inclined at 60 degrees, they can hold very large values of pull-out force, okay? But what we should understand that these forces develop for slip values that become increasingly large as the fiber angle increases. So what do we know? For a slip of 3 millimeters, in the real UHPFRC specimen, the crack is already localized. So we have already gone through the peak. We are already in the softening regime of the tensile curve. So although they can develop force, the force is not developed where you need it, which would be here for very small slips. Well, one variable that can describe this is the pull-out work. Okay, so this is the normalized pull-out work of many tests. This is the total pull-out work. It would be better to determine this pull-out work for small displacements only, but in any case, it does the job here. So you see that using this, it could be better to use some function a little bit more complicated. The thing is that you will never find fibers at 0 degrees. So theory says that fibers at 0 degrees, the probability is null to find fibers at 0 degrees. So you always find fibers with some inclination. So this part of the curve is not really that important. So what's important is here between 10 and 60, let's say. So a constant value, it's not a very poor representation of the reality, and it's very simple. And we adopted this. Well, and it's, as we will see, so we can determine under this assumption, we can determine the fiber efficiency factor from our image analysis of the polished specimens. And we have here the dots corresponding to the experimental values. So this plot relates the fiber efficiency with the fiber orientation. So what do we see? Fibers distributions with very large fiber orientation factors. The fiber efficiency factor is close or very near to 1. So all the fibers are effective. If you have very low fiber orientation factors, most of the fibers are ineffective. So you have less fibers crossing the crack, and most of those fibers are ineffective for the tensile response. So we proposed here a semi-empirical equation that allows getting the fiber efficiency factor if you only have the fiber orientation factor, which, as you will see, it will be very useful. So the description of the fiber orientation, it's done. Let's now go to the model that we have to really describe the tensile response of the composite. So the concept that we are using is based on the work of John West at the EPFL. So we basically model, we are able to model uniaxial tensile tests. So we consider that this is our control volume, okay, the test specimen. And how does this work? So we consider that the matrix cracking strength, it's randomly distributed here along the specimen. Okay, so you have here a number of parallel potential cracks, some of which will be activated during the loading process. Okay, as we will see, a crack very close to one that has been activated cannot be activated. We will provide some criteria for this. So some of the cracks will be activated during the hardening stage, and then until you reach the peak stress and one macro crack will form, the material will enter in the softening stage, and the remaining cracks will unroll. Okay, so we consider that in our specimen, the fiber content and orientation is all the same. We consider that these cracks can be idealized or modeled as an array of parallel cracks. Well, reality, it's a little bit more complicated. So sometimes you see here some branching, some tortuous shapes, but we are modeling this as parallel cracks. And yeah, the deformation is localized in this crack once the tensile strength is reached, and then at this point no more cracks can be activated because they're actually unloading. So the full model description can be found on this page. How do we simulate multiple cracks? Because the actual stress is constant on the specimen. So how do we allow for multiple cracking? As I told you, the tensile strength of the matrix is randomly distributed. We use a normal distribution with defined by a mean value and a standard deviation. So all these cracks have different tensile strengths for the matrix component. And then we also define a minimum crack spacing. Okay. So for those of you that are used to reinforced concrete design, you see some resemblance here with the average crack spacing in reinforced concrete. So you can think of alpha 0 times the volumetric fiber fraction as the effective reinforcement ratio that we consider in structural concrete, in reinforced concrete. But then we use here an extra parameter, which is alpha 2, that we call alpha 2. So if the fibers were rebars, so continuous filaments, this alpha 2 would be equal to 1.0. So, but the fibers are not continuous filaments; they have a small length, so they are not so effective in controlling the crack spacings as if they were continuous filaments. So this is a model parameter. So how do we use this? For instance, if this crack has opened, if the neighboring cracks are at a distance of this one smaller than the minimum crack spacing, we don't allow these cracks to open, and only the cracks that are spaced more than this value can be activated. So we need to describe the response of each of these cracks, and there are many of them on the specimen. So this is the behavior of a single crack. Starts at the crack opening of 0 and continues until complete fiber pull-out. So the total response at each crack, it's the sum of 3 contributions. This is based on the works of Victor Lee, here referenced in this paper. So the biggest contribution, the most important contribution is due to the fibers. Okay, it's the fiber bridging stresses. Okay, sigma. Okay. Of course, there's a small contribution from the matrix, very small. Okay, and a small contribution of what is called in the literature fiber pre-stressing, which is basically so the fibers that elastic stresses locked in prior to cracking, which then after cracking they are gradually released. Important also to note that the fiber contribution can be divided in 2 stages. So first we have a fiber activation stage where the forces in the fiber increase, okay? Or also called as fiber debonding stage. So the bond between the fiber and the matrix is being activated in this stage, and then suddenly the fibers start to pull out. Okay, the post-cracking tensile strength of the cracks is fairly given by the fiber contribution. Okay, so I will not go into too many details. So if I want the contribution of the fibers, I have to integrate through all the possible fiber orientations, through all the possible fiber embedment lengths. And to make this simple, so here you see the pull-out force of a fiber oriented at an angle theta with an embedment length LE as a function of the crack width. To make this simple, we will consider that this is the product of a function that does not depend on the fiber orientation times the fiber efficiency function, which allow us to mathematically simplify the equation that you see here. So the red part, it's only related to fiber orientation. It can be shown that the red part here, it's the product of alpha 0 times alpha 1, so the fiber orientation times the fiber efficiency factor. And then after the work of Thomas Thiel in Zurich, he developed a very clever closed form solution for this integral, which requires some simplifying assumptions, which basically you have a function that is a function of the crack width that varies between 0 and 1, and then a constant value over here, okay? Which is basically the post-cracking tensile strength of the material. Here you have the equation for this function for the debonding or for the fiber activation stage, and here for the pull-out stage. So here we have this value, the fiber post-cracking strength, or the maximum value of the contribution of the fibers. Let's look a little bit at this equation. So you see here a product of two parameters that depend on fiber orientation, but still related to fibers. The fiber content, the fiber volumetric fraction, okay. The fiber aspect ratio, so the length of the fiber divided by the diameter. So all this is fiber related. This can be lumped in a single scalar value, so what we call the fiber structure parameter. And this is the rigid plastic fiber to matrix to the bond strength that depends on the matrix and the shape of the fibers. So if this is correct, if this equation is correct, then I can plot the tensile strength as a function of the fiber structure parameter, and I would expect a straight line with the slope being the bond strength. Well, this agrees extremely well with what we observed in the experiment. So we measured all the fiber, the fiber orientation factors, the fiber efficiency factors in these specimens, and we see that actually the linear trend shows a very strong correlation. And then you have here some equations to describe the small contributions of the matrix and the fiber crystal. Well, how does the model work? So the model requires some material properties as inputs, okay? E modulus of the fibers, E modulus of the matrix fractal energy to get the contribution of the matrix, the fiber to matrix bond strength. Then some model parameters which are quite small. So the mean value of the matrix cracking strength. We say this is a model parameter because we introduce this as a ratio. Okay, the coefficient of variation of the matrix cracking strength and the crack spacing parameter, and then all the fiber related parameters, which are lumped in that fiber structure parameter that I just showed in the previous slide. So using this set of data that I showed here, you see what the outcomes of the model are for instance, different fiber contents, okay? You see that for a given fiber content, you have different curves. So don't forget that every time we run the model, we have a random distribution of the matrix fiber, of the matrix tensile strength. And for instance, different runs will lead to slightly different results, mostly on the crack formation stage. So how does this compare with experiments? Well, compares reasonably well. So you see here tests on UHPFRCs with different fiber contents, different fiber orientations, and with the same set of material properties, same set of model parameters, we could get a reasonable fit to what we observed. And if you remember, where do we came from? So we wanted a simple model to put in our finite element models that is bilinear, that is described by the conventional limit of elasticity, tensile strength, described by the strain at the onset of localization. And you see these three parameters here in these three plots as a function of the fiber structure parameter, that parameter that lumps all the effects of the fibers. And we see that the model describes this very well throughout a wide range of values of the fiber structure parameter, and even the mean crack spacing. Okay, here you see different specimens with different values of the fiber structure parameter, which correlates very well with the mean crack spacing. Okay, here large values of this parameter lead to very small crack spacing, so the specimen entered in the stabilized cracking stage. Here, most common in poorly or randomly oriented fibers, you have specimens in the crack formation stage, so the cracks start being more, the distance between the fibers becomes larger. And then, of course, if you have a single crack, crack spacing is undefined. So, how do we use this? So we must go from an isometry, so the description of the different fiber orientations with the different directions. We must go to the mechanical properties of the material. Using these models, it's possible. So here you have different distributions of the fiber orientation factor. So this is a polar plot. Okay. The red line, corresponds to a probability density function with very well oriented fibers. The blue curve, it's a probability density function with no preferential fiber orientation, in which the fiber orientation factor is constant no matter the direction. Applying our equation for the tensile strength, we can go from here to the tensile strength. Applying the model that I have described, we even can get the strain at the onset of localization on every direction. Okay, we can describe the anisotropic behavior of the material if the fiber orientation is relevant. So the good news is that we really don't need to use this meso-mechanical model, this meso-level model on our finite element analysis. We can use much simpler surrogate models. What does this mean? So we can see that we can derive very simple equations that can give us the parameter that we need. Okay, the strain at onset of localization, the conventional limit of elasticity, the post-cracking tensile strength. All this can be obtained with simple functions, which of course can be or should be calibrated with the meso-mechanical. So a small section now about the non-destructive method. So we saw that the orientation of the fibers governs the tensile behavior. It's good that if we could have a procedure so that we can measure the content and orientation of the fibers on the specimens that we cast. So we developed a non-destructive test method following the concept previously introduced by other authors, Ferrara, Pfeiffer, which is based on a U-shaped magnetic probe, okay, on which we induce a magnetic field. So magnetic field, it's a good idea to use here the magnetic properties of the steel fibers, simply because so if we measure the relative magnetic permeability of our material, we are sure that this is only related with the fibers, because the matrix, the relative magnetic permeability of the matrix, it's the same for engineering purposes of vacuum. No matter if you cast the element at 1 day, 2 hours, or 80 days, it's constant, it's always the same value. So any variation on the relative magnetic permeability, it's only related to it. So The probe is basically a ferrite core with some copper winding on which we introduce an electric current that generates a magnetic field. And the magnetic inductance of this magnetic field can be measured with this device. And it can be analytically expressed by this equation. The complex things here are the determination of this relative magnetic permeability of the composite. So we developed some models to have an estimate of a theoretical value for the relative magnetic permeability as a function of the fiber orientation. So this is described elsewhere. So we found this very ugly equation, but yeah, you can put it in an Excel spreadsheet that basically provides you the relative magnetic permeability as a function of the fiber content and orientation of the fibers. Of course, our fibers can have random orientations. We can generalize this concept to the cases where you have fibers with different orientations. So let's see how this compares to experimental evidence. So the relative magnetic of the UHPFRC can be obtained very simply by measuring the inductance of the circuit when the probe is placed on the air, and the inductance that is measured when the probe is placed over the UHPFRC. And we took measurements on many specimens with oriented fibers, non-oriented fibers. So, and we took measurements every 15 degrees. So, this is what the theory predicts, okay? So, every 15 degrees, if I have a specimen with the oriented fibers, I see higher relative magnetic permeabilities, and then they decrease when I am 90 degrees apart, and then they decrease again. So, the green curves correspond to a specimen with less fiber content, and the orange and the... So, this is what we get from the measurement. So it's not far away from what we predict with that complicated equation. So we see the same trends. And also very important, what do we see? We see that the theoretical model predicts that if we make the average between two orthogonal measurements of the relative magnetic permeability, so measurement at 0 degrees, measurement at 90 degrees, if you make the average, you get these lines that you see that are nearly horizontal, okay? So a good indicator of the fiber content, it's the mean of two orthogonal values, and it can be shown that it's independent of the fiber orientation, and good news, it increases linearly with the fiber content. And we confirm this with the measurements, okay? It increases linearly with the fiber content. What about an indicator of the fiber orientation? So we found out that this is a good indicator of the fiber orientation. So we take the same two measurements at 90 degrees, but now we use this equation instead. Okay? The model says that this is nearly independent of the fiber content. You see the model predictions for many different fiber contents, and it's almost the same curve. And this is what we see actually in the experiments. So it would be, what we want is to relate this now with the fiber orientation factor. This is what the model says. So the relation between this indicator and the fiber orientation factor that we need, it's like this. So if we use a range of fiber orientation distributions more close to what we can find in practice, we see almost a linear trend. Okay? And this is actually what we observe, okay? So we can find a linear relation between this fiber orientation indicator and the fiber orientation factor. So two linear relations, two orthogonal measurements, and we can get the fiber content and the fiber orientation factor on the point where we are measuring. And then we can use this data from NDT to predict the tensile strength, and we did it. So I've shown you this graph before, where we have our fiber structure parameter determined using time-consuming, expensive image analysis. And here we have the same results, but using the NDT data. And you see that the results are fairly close. So we don't lose a lot of information by using NDT compared to doing the time-consuming image analysis. The good thing also is that if you want to know the tensile strength along any direction, we can approximate the relative magnetic permeability by a second-order tensor, which means that we only need, if we want to know the fiber orientation along any direction, we only need to make 3 non-collinear measurements. Okay, this is how the tensorial approximation compares with the measurements every 15 degrees. So the agreement is quite good. So some examples to finalize. So here we cast a plate, nearly 1 square meter, 30 millimeters thick, theoretical volumetric fiber fraction of 3%. And here we have the results of our measurements. Here we have the contour map with the measured values of the volumetric fiber fraction. So the theoretical value was 3. We can see values ranging from, I would say, a little bit above 2.5 to a little bit below 3.5. Using the tensorial approximation, we can even plot the directions of maximum magnetic permeability, which should coincide with the directions of maximum fiber orientation. Okay? We can also represent this using ellipses, where the radiuses of these ellipses are proportional to the fiber orientation factors. So we cut some plates from this large slab, and we tested under 4-point bending, and this is where the cracks appear. In the governing crack, the final crack appeared in the 4-point bending test. So I plotted here the locations where the crack appeared with the non-destructive test-based estimates of the tensile strength in the horizontal direction and the tensile strength in the vertical direction. And you see that the cracks appear where we see that the tensile strength is lower. Okay. Sometimes the agreement is not perfect because the roughness of the plate on the free surface side was such that the thickness was not really constant throughout all the slab. This is the full range of results in the 4-point bending tests, and we did some inverse analysis, and this is how it compares the result from the tensile strength from the test, the result from the tensile strength estimated by NDT. And we can use Diana also. So we can try to simulate the behavior of these 4-point bending tests using the information that we retrieved from NDT. So each block that you see here corresponds to the area of influence of one single NDT measurement. Okay, and we introduce different properties in each block according to the NDT data using the bilinear functions that we have described before, which are fed. They get data from the NDT test method. So we use the total strain rotating crack model. We are introducing the constitutive law that is suited to the behavior in the horizontal direction, okay? Because it's the direction on which the beam works. And here you see the results of the simulations of some points. So in some cases, the agreement was very good, as I show here. In others, not so much, but typically the agreement is quite good. So the outcome of this is that we can get data from NDT that can be used in finite element simulations to get the real behavior of the material as placed in the structure. So this method is being used by the industry already. So I key here an application by Preford, which is a precast company in Spain, specialized on UHPFRC, which is using this method for quality control of their elements. Here you see the estimate of the volumetric fiber fraction of 4 panels that were cast with different fiber types and fiber content. The estimate of the fiber orientation factor. So here you don't see values that deviate too much from 0.5. So the orientation of the fiber is really random. And here the directions of maximum and minimum fiber orientation factor. So some conclusions. Here the domain is really happy because it's really possible to model the effect of fiber content and orientation on the tensile response of UHPFRC. Simple surrogate models can be used to obtain the parameters for simplified constitutive laws that can be used in nonlinear finite element structural analysis. And the fiber content and orientation in thin UHPFRC elements can be obtained using non-destructive test methods, which can feed the surrogate model. Well, this cannot be used if you have rebars distributed in the UHPFRC layer, because this would affect the NDT measurements. Okay, so the non-destructive test method only works if you don't have any rebar on its vicinity. So future developments of this. So we are planning to implement these ideas in a dedicated model for UHPFRC using the use supplied subroutine feature, and then validate against experimental tests in which the crack orientation is not known beforehand, because in the simple beams that we tested, we knew that the behavior is longitudinal, so we knew which was the tensile response that we need to introduce. So this is what we are planning to do in the future, and I would be happy to answer some questions. Thank you.
Thank you very much, Mario, for this very comprehensive presentation. And yeah, it was very interesting to see how you start from experiment and come to a potential material model in Diana. So yeah, we are definitely there to assist you when you are at the stage of developing this user-supplied subroutine. We have exceeded 1 hour, so I'm not sure if I can take questions. There were some questions about how you control the orientation of the fiber, but that was early question, and I think most of them have been replied during the presentation. So what I suggest, I'm going to collect the question, and I'm going to share the question per email with Mario. So Mario, at your earliest convenience, you can look at the question and get back to the person who was asking the question. I will provide you all the details because I don't want to extend too much this webinar, because some people have to leave. But there's also a lot of compliment for your work, and this is important to raise. There was a high interest for this presentation, and people are really thankful for the nice presentation you did, Mario. And I would associate Diana and speak on their behalf, but we were very happy to have you first as a Diana user, but also as a guest lecturer for this technical webinar today. And this is quite a research work, and yeah, we are definitely looking forward for the next step. So having said that, I think I'm going to end this webinar for today. So as I said, I'm going to share the question with Mario. And yeah, Mario, feel free to get back to the person directly. I think there are just one or two questions that still need your attention, but the rest, I think, was clarified during the presentation. I mean, people were just impatient in asking some of the questions.
Sorry, I took too long.
No, I mean, I could feel. I mean, that's the point. I mean, you speak with passion, and that's you could speak for hours about this topic, I'm sure. So that's really great. That was really great, and it make it very interesting to follow. So thank you for that, Mario. It was really great presentation. So I'd like to end this presentation, and once more time, thank you to Mario for the time he spent preparing and giving this presentation. As I said, I will share the question with him, and he will get back to you. And we are also going to discuss with Mario about the video of this webinar. And when everything is fine, we will publish it on our YouTube channel, so it will be available within a week or so. So one more time, thank you very much, Mario. And thank you to the whole audience. I mean, it was quite an audience today, so quite some interest for this topic. And please keep an eye on our website. There are more events and courses coming. There is our regular RC course coming next week. So if you want to attempt, don't wait too long, because we start on Monday. And we will have also more webinars in the coming weeks and months. So just keep an eye on our website. And thank you all for attending this webinar. I wish you a nice end of the afternoon or early morning, depending where you are located in the world. Thank you all. Bye. Thank you, Mario.
Thank you. Thank you.